This is a video to explain how to differentiate functions that are defined by Cartesian equations. So when the first order differential equation is introduced, sometimes the solution is represented by the Cartesian equation as a part of exact solutions, not just a function written in x variable alone. So here's an example. So for example, sine of xy time equals x plus y. This is the Cartesian equation, so x and y are just numbers in xy plane, so coordinates of an xy plane. But when you sketch the graph of this Cartesian equation, it forms this graph. As I shaded here, if you look at just locally this part, it can be the graph of a function, since it passes so-called the vertical line test. Or you can take that piece and take that piece and so on. So we call it a locally graph of a function. So this is what I wrote. This can serve as exact solution of differential equations, and this Cartesian equation is now differential equation called the exact solution, and we can look at this graph as a function of x and y. Or mainly shaded this part just to show that portion is a graph of function of x. Sometimes we have to consider x as a function of y, which is this part. If you happen to look at the point which happen to have a vertical tangent line, I don't know if you can see that or not, here's a vertical tangent line there. There's no way you can choose a portion, if it is like this, around that point, such that that portion passes that vertical line test. So in that case, we have to look at this as a function of y variable, and x is a dependent variable. So locally, this graph of a function, often its graph of an equation can be interpreted as a graph of a function. But you can imagine there are infinite folds of complicated part may show up. So in general elementary functions, you don't expect that kind of thing to show up. So often in the examples we look at, can be looked at as a graph of a locally graph of a function of variable x or variable y. So before we actually go and think about this as a function, this equation defining a function of x, and this statement, the Cartesian equation defining the function, not just by looking at the graph, and there's a theoretical version which is called implicit function theorem. I moved it a little bit so that you can see by implicit function theorem, and it takes a while to state this one correctly, and it actually requires several variable functions, a theory on several variable functions. So I'll just quote it here. Whatever the condition is satisfied here, and via this implicit function theorem, we can look at this as locally a function of x in many parts. Now with that, our question is now, if the function is defined like this in calculus 1, is often said implicitly defined. So how can we differentiate this function implicitly if it is implicitly defined? As you all remember, this is called the simple chain rule, because when you differentiate, well, this is called, first of all, functional equation. That was a Cartesian equation before. Once you look at y as a function of x, this becomes a functional equation. So these two functions are equal to each other, so derivative must be equal to each other. And when you differentiate with respect to x, and you have to go through this y, and whenever you differentiate y, you have to carefully use the chain rule. So let's first differentiate this left-hand side, because the most outer function is the sine, so we differentiate that as a one variable function first, and we have to differentiate inside, which is x, the monomial, the linear function, times the implicitly defined functions. When you differentiate product of two functions like this, you have to use the product rule here. So that's why it looks like this. The derivative of x times y, it's product rule, derivative of x and derivative of y, which we don't have a formula. That's the whole question here. So we can write it as y prime of x. And this functional equation gives us an idea about what kind of y prime of x what kind of equation y prime of x satisfies. So if you look at the right hand side as x plus y, so it's going to be 1 plus y prime, which is written here, 1 plus y prime. So that's the functional equation derived from this functional equation by differentiating. So we have one functional equation, differentiating both sides gives us another functional equation. This time it involves derivatives. I'm being sloppy here, and that did not work out what this y prime is, but you will see the answer later on. So what you will do is that expand this one and collect the terms that has y prime in it, which you will have as you expand cosine of xy attached to it, and this one collected on one side. Everything else that does not have y prime in it, which is 1, and this y times cosine xy will be collected here, and so on. So that's how you do that in calculus one way. And I'm about to introduce in a slightly different way, and that'll result in a slightly faster method. And the whole purpose is to explain why this faster method works that way. So different approach I was talking about was this called the parametric equations. Let me adjust it a little bit. Right, that looks better. So this was called the Cartesian equation. Now, again, using the implicit function theorem, you can look at this as the equation of the function x and y. Both are parameterized by auxiliary variable t. Interesting thing is that you can assert now, we can globally, so I'm not showing the complete word, but this says globally we have a parameterization. So if you're looking at that -3 by 3, the picture that I showed earlier, that entire graph can be realized as a function of x and y there. So there are two functions, so that these two functions satisfy this functional equation where the main variable is neither x or y, but this auxiliary parameter t. So that's a parameterization of this graph, of this Cartesian equation. It's a convenient notation. This t usually in physics represent time, so that's the main use in many applications in differential equations. So especially the variable involved here, x and y, viewed as a function of time, its derivative with respect to the time will be just simply denoted by this x dot and y dot over there. So we learned that in calculus 1, or actually in the second sequence of calculus 2, calculus, that when we look at this y as a function of x, which is how we approached it earlier, we can write that slope dy dx in terms of these two quotients, these two quantities. So I squeeze in here so that I can see everything. So there, when we look at y as a function of x, that slope of the tangent line there can be calculated as the rate of change of y divided by rate of change of x when it's a parameterized with respect to t. So here's an example right here. The equation is so small in there, but it says x squared plus y squared equals 1. And this Cartesian equation, we have very explicit parameterization for which we can test this or review this result right there. So what this x dot and y dot is representing, if you put these two together and to form a vector form, this becoming x component of a vector, y component of the vector, that vector represent velocity vector right there, and that velocity vector is supposed to be tangent to the graph here. That tangency is the statement. So establishing this one requires literally mathematical work, but it's just a statement I'm stating here, so that velocity vector is really geometrically, it's a tangent vector in there, which is written here. So that's one way to compute. So what we're going to do, we differentiate and get this x dot and y dot come out, and see if we can rewrite those equations into this form: y prime x prime y prime y dot divided by x dot. First step is differentiating both sides like before, but notice that this time is with using t variable. So I won't repeat the product rule and chain rule stuff, but when you do the differentiation of x times y, this time product rule goes like this. This x is not going to be 1 because we're differentiating with respect to t. So this is what we have. On the right hand side again, since we're doing with respect to t, we're going to have x dot plus y dot. the next step is that you're collecting all the x dot and y dot such that we can compute this quantity. So if you collect the x dots, and this is the term together with this one, and there's x dot, if you collect all of them, x dot is factored out. If you collect all the y dots, and y dots factored out, and the rest of the part looks like this. So from here, we can definitely compute y dot divided by x dot. So here's the rest of the part. If you take this quotient, if you do the algebra, y dot divided by x dot, which is supposed to be dy dx, and it gives you this quantity. So if you know the x coordinate and y coordinate at that point, and we can calculate the slope of the tangent line. But before you enter this part here, the mathematicians thought that this is a very nice form to play with, where everything is kind of even and not unfair to the one variable and another. There's x and y pretty much playing the same role here, so that's very symmetric. That's what they call symmetric nice equation. So here's how you put it into dy dt dx dt notation, so exactly the same thing with the dx dt and dy dt. So this part is mathematician's notation. And next part is also showed up in many engineering and physics textbook, and its correct foundation takes a little bit of time to introduce. So we will just use this expression here. It makes perfect sense to us. X and y function of t, so dx dt and dy dt, and x and y function of t. This makes perfect sense. But often you will see this exact same equation missing this dt in there, which is this equation right there. It's not actually showing the dy, but it has a dy to it. But you can see that there was a dx over dt, and it's missing a dt. So it just makes no sense. And often in non-mathematical text, sometimes this was replaced or kind of interpreted as a delta x, but delta x is delta x, and dx is something different. So the way I'd like to introduce is that when we look at this equation, we can just exactly look at that equation of this form. Actually, this is a shorthand notation, mathematician's shorthand notation for x dot, where we understand the variable there is some parameter. One variable parameter is involved in here. So this dx itself is called a differential form, but you can look at it as this dx dt and dy dt, the first order derivative of with respect to the auxiliary variable. So when you look at it here, and to put this one into practice, you actually have to put this one into dx dt, and that'll make more sense. So from here will be the method of calculating that differential form of the functional equation that involves a derivative, differential form of a differential equation, using the so-called the partial derivative method. The first thing we have to do is that if this is the Cartesian equation, we have to move additively or subtract things so that we have right-hand side is 0 and left-hand side is something in terms of x and y. And we call that function here, the entire thing, as a two-variable function. So where x and y are both independent variables, not dependent variable of any auxiliary function, just a two-variable function. So the following process is called taking the partial derivative of this function. So we have this function where x and y are both variable, and first we look at this expression and treat this y variable as a function. So one thing you can do to make this one smooth is to replace that y with the transcendental number pi, so it's x times pi, or pi times x. This one will be x plus pi. Think about how you would differentiate this function with respect to x, and treating, of course, y as constants like pi. So I'll do that part for you. So you're looking at here, we're differentiating cosine, sine, so it becomes cosine. We leave that inside of the sign, xy, and we have to differentiate inside. Remember, y is treated as a multiplicative constant, so if you differentiate this one with respect to x, y is the answer, so you have to multiply the y, which is called the chain rule. And this part here, if you do that with respect to x, is definitely just 1. Y is treated as a additive constant term, so it becomes a 0. Now let's do the same thing. This time we're treating x as a constant, so x becomes constant like pi, and that part becomes pi differentiated with respect to y. So answer is this one. The sine becomes a cosine, that part is the same. Derivative of inside this function, this time is just x treated as a constant, and this one here is -1. So this is a result of differentiating this one, leaving y as a constant, and this is a result of differentiating this one, leaving x as a constant. After write those two down, all you have to do is just put this dx and dy in here. So like this. So that's exactly the same result that I was trying to show using the derivatives of parametrization. So this is a general notation. What we just did, you take that expression f and differentiate it with respect to x, leaving y as a constant. That part here, this part here, is denoted by this curly d f divided by curly d x. This is a partial f divided by partial. It's also called df dx, but in the context we do understand this is a partial derivative, and this one is done with respect to y, leaving x as a constant. So that's the quick answer I was talking about. Differentiating this one, while x and y is a function of one variable, like the parametric equation we saw there before, it is done in this way, and it results in a correct functional equation. That part, what we just did here, is called also the chain rule, because it sense what's involved in here is basically the going through the chain rule in with one more variables. So this one is also called the chain rule of two variable functions. So proving this statement here appropriately requires this analysis of two variable function and a little bit of a Calc 3 technique. So that's not what we're going to do here. What we're going to do here is that for our differential equation course, what we're going to look at is mostly this function made out of these basic elementary functions. So I will explain why this one works like this for the case of this elementary function. And that part is not very difficult, and it's also interesting to see how this plays out. So in the next video, I'll explain why it works like this.